Okay, welcome everyone to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim R&D Manager and the Associate Director of the National Center for Simulation and Rehabilitation Research. I'll be serving as the moderator for today's webinar. I'm pleased to welcome our presenter for today, Ravi Balasubramanian, who's joining us from Oregon State University. So a little background before we get started. Next slide, please. OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating the movement of humans and animals and robots. The application includes a wide set of tools, including general purpose inverse dynamics, optimization to estimate muscle and joint forces, methods to create simulations for motion capture, and then tools that allow you to analyze and visualize the results of simulations. So the first goal of our webinar series is to showcase the cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate. Before we get started, a few reminders about the webinar format. Next slide, please. So questions will be addressed at the end of the presentation using the Q&A panel. Also, if you need any additional technical help or have issues, you can consult the guide on our website. Now I'd like to go ahead and introduce our speaker for today. So Dr. Balasubramanian is an assistant professor in the Department of Mechanical Engineering at Oregon State University. There he directs work in the Robotics and Human Control Systems Laboratory. He's received several awards, including the Best Student Paper Finalist Award at the International Conference on Robotics and Automation, and he's also the recipient of an Outstanding Researcher Award from our National Center for Simulation and Rehabilitation Research. So the key principle behind Dr. Balasubramanian's work is to simultaneously draw inspiration from the human control system to advance robotic systems, and then to use these robotic systems to develop a better understanding of the human body and improve quality of life. So in his talk today, he will explore how he's combined experimental studies with simulation and OpenSim to design and evaluate a new hand tendon transfer surgery. So we're pleased to have you today, Ravi. Please take it away. And do remember to unmute your microphone as well.
Just did that. Thank you, Jen. Can you hear me?
Yes, I can hear you loud and clear.
Great. Thank you. Hope everyone is having a nice day wherever they are. It's a delight for me to present to the OpenSim community on some exciting work that's going on in my lab at Oregon State University. And the overall idea is to explore the use of implanted engineering mechanisms in hand tendon transfer surgery. This is joint work with Professor Christopher Allen, who's a hand surgeon in the University of Washington. And regarding OpenSim, we have been, my group has been using OpenSim for about a year and a half so far, and we are really thrilled with how we have been able to combine simulation studies with experimental studies. Okay, just some very quick background on who I am. I did my schooling in India, after which I did a bachelor's and master's in engineering in Singapore. I did my PhD in robotics at Carnegie Mellon. And then I developed some interest and expertise in human control systems during my postdoctoral fellowship in neurobotics at the University of Washington. And I was also a researcher at Intel for 1 year. Then I moved to Yale University as a research scientist exploring mechanism design for robotic hands. And now I'm at Oregon State University directing the Robotics and Human Control Systems lab. Robotics, of course, is to design intelligent machines that can sense, think, and act. while on the other hand, human control systems, the way I look at it is to treat the human body as a control system with actuators in the form of muscles, with sensors, and a smart controller in the form of the brain and spinal cord system. So with these two themes, this spawns a variety of different projects in my lab in the areas of robotic manipulation, design of robotic mechanisms, human neural systems, biomechanics, and learning in the human body, control and dynamic systems, and mobile robotics. As Jen was mentioning, the overall theme of work in my lab is to try to truly integrate robotics and human control system study. So we study the biological system, for example, the human hand, and try to draw inspiration and transfer the tried and tested solutions from biology into robotic devices, such as the robot hand. And at the same time, because studying the human biological system is pretty complex, for example, the human hand alone has about 35 muscles in it and has 17,000 sensors in it. What we do is we build robotic devices from which we can derive explicit physical models and mathematical techniques to derive insight into the biological system, such as the human hand. Usually, most of the research goes in the direction of the upper arrow, where we draw inspiration from biological systems to improve robotic devices. But in this talk, I will show you an example where we have been inspired by engineering mechanism used in robotic hands to improve human hand function. Okay, so which brings me to the topic of today's talk, which is tendon transfer surgery. There are a variety of tendon transfer surgeries, some for the upper extremity and some for the lower extremity. In my work, currently we focus only on hand tendon transfer surgery, which are performed for a variety of conditions such as stroke, palsy, trauma of different types, and congenital defects. And the overall idea, if you can see my mouse, is that you read out tendons from a damaged or a non-functioning muscle to a new muscle. So in this example, you read out, in this particular tendon transfer surgery example, you read out all 4 FDP tendons, which are to the ECRL muscle, which is a wrist muscle. Okay? And the overall goal is to restore lost hand function. So if the FDP was not functioning, then you transfer the tendons to the wrist muscle, which may still be functional. In terms of the potential impact of our work, we estimate that hand tendon transfer surgeries, the market is about $200 million in the US alone, and there are about 20,000 surgeries per year in the US, and this has been extensively used in the military since World War II. So, but there's a problem with the state of the art. The state of the art is that attachments between muscles and tendons are made with sutures, okay? And in some scenarios, it leads to poor hand function. And I will illustrate this as the talk proceeds. The key idea we are trying to explore is to use engineering mechanisms such as pulleys and other engineering mechanisms in place of the suture to connect the muscles and tendons with the goal of improving hand function. And I will illustrate this in the context of tendon transfer surgery for high median ulnar palsy, which is one of the most commonly performed tendon transfer surgeries today. Okay. So before I proceed with the details, let me give you a very quick overview of hand anatomy. There are about 35 to 40 muscles in the human hand, in the forearm and in the palm of the hand. But 2 of the muscles are the flexor digitorum profundus muscle, which creates finger flexion movements, and there are 4 bellies which and each of those bellies is connected up to each of the 4 fingers. And the other muscle, another muscle in the forearm is the ECRL muscle, or the extensor carpi radialis longus muscle, which creates wrist flexion, wrist extension movements. Okay, and these 2 muscles are innervated by the ulnar nerve, the median nerve, and the radial nerve. Okay. So all 4 muscle bellies in the FDP muscle are innervated by the ulnar nerve and the median nerve, whereas the ECRL is innervated by the radial nerve. Now, unfortunately, what happens in median ulnar nerve palsy is that the ulnar and median nerve are no longer functional, and this could be either due to a palsy or due to an injury. Okay, and what this means is that the person loses the ability to flex the fingers. Okay, and this results in poor grasping capability and an inability to perform even the basic activities of daily living. So the current tendon transfer surgery for median ulnar nerve palsy is to say, well, it's only that the FDP muscle is no longer functioning because the median and ulnar nerves are no longer functioning, but the ECRL muscle, which is innervated by the radial nerve, is still functioning. So the idea is to suture all 4 FDP tendons to the ECRL muscle. Okay. Now, while this looks simple, this actually has some disadvantages to it. Now, this procedure allows the person to move their fingers in a coupled fashion, as though you're waving bye-bye to somebody. The problem is that this coupled finger movement affects grasping tasks. Okay, because now if one finger makes contact and with the object and stops, the other fingers also have to stop because of the coupled movement. And then the user has to now stretch the tendons in the finger that has already made contact to cause that finger to flex and cause the other fingers to flex as well. Okay, so overall this results in very poor hand function following the current surgery. Right. Now, the key idea we are proposing is to replace the suture with this simple passive miniature pulley mechanism. Okay, and implant that mechanism in the forearm. Okay, so this mechanism actually belongs to the class of differential mechanisms. Okay, where there is only one input in the form of muscle force and movement from the ECRL muscle, and that input is getting distributed across 4 FDP tendons. Okay, and now the key idea is that the additional freedoms provided by these pulleys enable the fingers to fully close on the object. So even if one finger makes contact and the muscle keeps contracting, the pulleys will slide, will translate and rotate inside the forearm passively to allow the other fingers to wrap around the object. We term this behavior of the fingers enabled by the pulleys adaptability, meaning that the fingers are adapting or conforming to the object shape. And because of this natural adaptation, this actually we expect will result in significantly lower force requirement of the ECRL muscle, because there's no longer a need to stretch the tendons of the fingers that have made contact to close the other fingers. Okay, so this is how we expect that the proposed pulley-based procedure will help improve hand function. Okay. Now, the inspiration for use of these pulley mechanisms in tendon transfer surgery came from the use of these mechanisms in robotic hand design. Specifically, there are these under-actuated robot hands which use significantly fewer motors than degrees of freedom. And so these differential mechanisms such as these pulleys and 4-bar linkages are used to adaptively transmit force and muscle and motor excursion from one motor across even say 8 joints or even 16 joints. Okay, so all the intelligence is embedded in the mechanical mechanism. Okay. And we are trying to do the same thing in the human hand itself through tendon transfer. So sorry, just a couple of examples are the SDM hand from originally Harvard University, but now at Yale University, and I have designed some of the mechanisms for underactuated hands when I was at Yale University. And another example is the SARA hand from the University of Nevada. Okay. Now, with this as the introduction, let me give you some a quick snapshot of the results that we have obtained through cadaver studies and simulation studies using OpenSim. So we did a cadaver study with 6 cadavers. And this is an old design of this hierarchical pulley system with off-the-shelf components. So we have slightly big-sized pulleys. The proximal pulley is connected up to the ECRL muscle. The distal pulleys are hooked up to the FDP tendons, and there is a cable going between the proximal and distal pulleys. And we did a study where we created movement in the cadaver using a linear servo, which tugged on the ECRL tendon, and we had these cameras observing the finger movement, and we want to show that the hand function is improved in grafting tasks specifically, because grafting is such a fundamental aspect of the activities of daily living. So we had the hand try to wrap around a ball, and markers were placed on the fingertips, on the fingers, and these cameras gave us joint angle changes during the grafting process. And there was a force sensor placed inside the ball to measure how much force was applied by the fingers on the ball. And there was also a force sensor placed between the linear servo and the ECRL tendon, which gave us a measure of how much force that the servo was applying on the tendon itself. Okay. So if you're interested in a newer design, please feel free to contact me. Okay, so here I'm showing a couple of videos from the cadaver study. On the left we have the suture-based procedure, and on the right we have the pulley-based procedure. And the key point I would like you to note is in the suture-based procedure, the fingers move in a coupled fashion before making contact as well as after making contact, which leads to early slip of the fingers off the object. So there is coupled movement before contact, and then coupled movement after contact as well. Now, in the pulley-based procedure, we see coupled movement before contact, which is what we expect, because you still have only one muscle pulling on 4 tendons. But after contact, we notice that the fingers are adapting significantly better to the object shape when compared to the suture-based procedure. Okay, so what we did is we took these videos and actually created line drawings from them to illustrate this point a little bit better. So this is actual real reconstruction of real experiment data. So in the suture-based procedure, in this particular trial, we know it was the middle finger that made contact, Okay, and then the ring finger made contact. But what is happening is that during the grafting process, the middle finger is forced to slide on the object and go from the sphere to the neck region. Okay, and also the ring finger also is forced to slide because the middle finger is colliding with it. Now, in contrast, in the pulley-based procedure, okay, in this particular trial, it turned out that the pinky made contact first, and then the index finger, the middle finger, and then the ring finger. But the key point I want you to note is that there is significantly lesser slip of the fingers on the object during the grafting process, which is really what you want. Because if the fingers start slipping, then the user has to reorient their hand, wrist, or arm to ensure that they have a full grasp on the object. Okay. Now, just give you a quick snapshot of the cadaver results from 6 cadavers. If you want more detail, please feel free to contact me. But the basic point is that the pulley-based procedure led to 42% reduction in the actuator force requirement during the grafting process when compared to the suture-based procedure. Okay, and this is 42% on average, but for each cadaver also the actuation force requirement was lesser. Now, in terms of finger movement, what we noticed was that from the data, the angle data which we collected, we noticed that there was significantly reduced slipping during the contact process, and this was measured in terms of how much the joint angles changed during contact. So for the pulley-based procedure, it was much better. Now, also importantly, it turned out that there was no difference in finger movement before contact for the pulley-based procedure when compared to the suture-based procedure. So what this means is that the pulleys did not affect finger movement before contact. And overall, over these 6 cadavers, we had a significant result with p-values less than 0.05. Now, in addition to cadaver studies, we did simulation studies as well. Here, our key goals in using simulation was to broaden and speed up analysis across all the variables and designs in the study, in this problem. So also, I want to highlight that cadaver experiments are very expensive in terms of time and money, and also we had to do these experiments in Seattle for us and while we are currently in Oregon. So it takes us about 10 days to actually to make it happen. So simulations would be definitely a significant benefit for us. Now, another advantage with using simulation study is that we can perform a sensitivity analysis, of which I will show a couple of results in this talk. And we used OpenSim for our simulation study because of its the features available in it, the anatomy that was provided, the biomechanical models, and the large user base. And we really hope to be releasing some of these models for the community to be using in the near future. Okay, so we modified the Stanford VA upper extremity model to study the problem. In the suture-based procedure, we just took all 4 FDP tendons and connected up with the ECRL muscle. In the for the new proposed procedure, the differential mechanism-based procedure, we used a seesaw mechanism instead of a pulley mechanism because it's easier to simulate than a pulley system, but it has exactly the same effect. There is a proximal seesaw mechanism, and the seesaw mechanism can translate up and down in the forearm. Proximally and distally in the forearm, and it can rotate about the point at which it is hooked up to the ECRL muscle. So it has multiple degrees of freedom. And similarly, the distal seesaw mechanism also can translate and rotate. So it has exactly the same effect as the pulley systems, but it's just easier to simulate without having to simulate like tendons wrapping around round surfaces and so on. Okay, so I want to give you a couple of quick videos of the simulation study in OpenSim, and I want to highlight here that here we assume that once the fingers make contact with the object, they don't actually slide on the object. So it's a little bit different from the cadaver experiment, but then it tells us a really good measure of how well the suture-based procedure and the seesaw mechanism-based procedure are allowing the fingers to adapt to the object. Okay, so here's the video. The suture-based procedure, we have the ECRL muscle contracting, and we notice that once, let's say, the ring finger makes contact, the index finger has no chance of making contact because there's no slip. In contrast, in the seesaw mechanism-based procedure, the seesaw mechanism allows the fingers to adapt to the object shape so as to get a full multi-finger contact. Okay, here is just a snapshot of how the joint angles change during the grafting process. And so on the x-axis we have time, and on the y-axis we have the combined joint angle change for each finger. So we are adding up the joint angle change for the MCP, the PIP, and the DIP joints. And the point I want to take from the suture-based procedure is that as soon as the ring finger made contact, all the other fingers also stopped. Okay, and so this shows very poor adaptability for the suture-based procedure. In the pulley-based procedure, we noticed a staggered contact, which is really what you expect because you don't know which finger is actually going to make contact with the object because of uncertainty in finger positioning and uncertainty in the shape. But what we notice is that each finger is able to establish full contact with the object, and so you end up with 4 contacts between the object and the head, okay, which is really what you want. Okay, so we try to push this result a little bit further while in using in investigating if the pulley-based procedure actually or the seesaw mechanism-based procedure actually improves the robustness of surgery. So what do I mean by robustness of surgery? Here I'm referring to the kinematic robustness or the reduced variation in the joint angles to uncertainty in the surgery as well in the grafting task. So if I can explain this a little bit further, the surgeon, for example, has to very carefully choose the tendon lengths before completing the surgery, right? And this process is called tendon tension. So if the tendon tensions are not accurate, then one finger would make contact with the object before another finger, and this would lead to the same non-adaptive finger grafting, which I've highlighted. Now, the same sort of poor robustness can also occur due to variation in finger momentum. So moment arms in the tendon moment arms define the mechanical advantage of each tendon over a joint. And so the important point to note here is that these moment arms actually change depending on joint configuration. And so if the surgeon was not careful in choosing the tendon length again for this large variation in moment arms, then this can lead to poor grasping capability as well. And similarly, if there are errors in hand positioning, that can lead to poor grasping capability. So what we did in our study is that we varied the tendon length by 5%, we varied the finger moment arms by 5% and changed the hand position with respect to the object center by a few centimeters. And we wanted to see, well, now if the fingers did not slip on the object, what kind of variation in joint angles would we actually see? Okay, so again, we used summation of the joint angles for each finger and then summed up all those sums across for the entire hand. And what we noticed is that so on the x-axis we have the time of the grafting process, and on the y-axis we have the sum of joint angles. And we notice for the conventional procedure there is a large variation in joint angles for these for uncertainty arising from these three cases. Okay, and whereas for the suture based or the for the pulley based or the seesaw mechanism based procedure, there was a very small variation in the joint angle. So what this means is that for a patient after the surgery, it's just not clear after the suture based procedure how much the fingers actually have to flex. And so this can make it hard for the person to relearn how to use the muscle to perform grafting tasks. Whereas in the pulley based or the seesaw mechanism based procedure, it leads to very small variation in joint angles. Okay, now with this I am ready to give you a take-home message for my talk. So this is the first time that implanted engineering mechanisms have been used in are proposed for hand surgery, and first time that somebody has done studies in simulation and cadavers. And I want to highlight here that what we're doing here is really fundamental. Sutures have been the standard in surgery for 30,000 years, and I repeat, it's 30,000 years. There's no typo here. And what we're trying to do is replace the suture with engineering mechanisms to lead to better hand function in some cases. Okay, so that's the first take-home message. The second take-home message is that the pulley based procedure leads to improved hand function in terms of force requirement. And so if a person was using 100 newtons after the suture based procedure, they could actually use just 55 newtons, so which is a big difference. And also there's lesser slip of the fingers on the object during grafting. And we're also seeing that it leads to an improved robustness of surgery. Okay. Now we have some ongoing work in trying to characterize the grafting forces from our cadaver data. Okay. Now with that, I'm ready for questions. I just wanted to thank a bunch of people. For Chris Allen. We've also started working with Professor Buddy Ratner from University of Washington on designing biocompatible implants, and I thank people in the Harborview Medical Center and Brian Day and Joseph McGuire for very useful referral. So with that, Jen, I am done with my presentation. You can now move on to the remaining questions.
Okay, great. Thank you, Ravi. That was a great talk. It was a really interesting combination of experimental work with cadavers and simulation work. We'll go ahead and get started with the Q&A session. So all of the questions will be text-based. So find the Q&A box in your WebEx controls. It should appear in the bottom right of your screen. Type in your question and make sure you select to ask all panelists. So go ahead and enter your questions while we're waiting for those to come in. Oops, I have to bring up my Q&A panel as well. While we're waiting for questions to come in, I'll go ahead and ask one to get started. I was wondering what you think about scar tissue formation and how that might affect the pulley-based surgery versus the suture-based surgery, and if that's something you've thought about simulating and analyzing its effects similar to the robustness to surgical technique.
Right. This is a very important issue, which we are looking into. Now, one of the important, so there are two, so related to this car issue is the fibrosis thing, right? So as soon as a foreign body is placed inside the human body, then the biological system is trying to combat it. And so this is where biocompatibility becomes a very important issue. And Professor Buddy Ratner has been exploring coatings on top of biocompatible materials themselves that significantly reduce fibrosis. And so he has some Nature papers on this topic, and I would recommend that people review those papers. But basically, he has shown that even after 3 months of implanting a biocompatible material with this coating, there is significantly reduced fibrotic growth when evaluated on a rat example. Right. So we are looking into that, and I think it would be a terrific idea to explore this in simulation as well, in parallel with experiments, but we have not done that yet.
Okay, great. So Carrie Peterson asked a question you've already answered about, what materials you thought about using for the implant. And so a follow-up question she has to that was whether you expect tendon slipping from the pulley to be a common problem needing surgical repair.
Tendon slipping. So I don't specifically understand what you mean by tendon slipping. You mean slipping of the tendons off the pulleys?
Yes, I think that's what she means.
Okay, so yes, we'll have to carefully design the pulleys that prevent that. So we can, for example, wrap the tendons around, wrap the pulley, shape the groove in such a way that the groove wraps around the tendon, and that way there will be much lesser chance of the tendon slipping off the pulley. And regarding how the biological tendon and so we hope to use, we plan to use biological tendons as well as, we plan to use artificial tendons inside the mechanism itself, and not have the biological tendon wrapping around the pulley, just to make sure that prevent the chance of the tendons getting abraded and so on. So if we use artificial tendons, we can test that better. And so we are also looking into ways of attaching the artificial tendon to the biological tendon, so that you minimize chances of the pulleys losing, the tendons losing contact with the artificial tendon.
Okay, thanks. Now an interesting question from Aditya Thakur. How do you expect the advances in myoelectric control of exoskeletons and orthoses? How do you expect these advances will complement or compete with the research study that you've presented?
Okay. I think one of the strongest points of our work is that the system is completely passive. So what this means is that there is no, this pulley system is purely mechanical. It requires no power from outside. It requires no control signals from outside. We are still taking advantage of for example, the ECRL muscle's capability to create finger movement. So I think that is a very big advantage where you don't have to worry about external power, external control signals. Now, having said, I think that can be pushed significantly further just using passive systems. Now with electrical, myoelectric or other electrical or sensor-based technologies, I think the sky is the limit. I think there is a lot of scope there, but ultimately you want your purely mechanical system to work well on its own before you add on more features, before you add more bugs.
Okay, thanks. Now a question about your use of OpenSim. This is from Puya Amiri. So how did you use OpenSim for forward simulation? And in particular, how did you set the activation of the muscles?
Yeah, we used just very simple forward dynamics. We just for the ECRL muscle, we just used a ramp function over like 2 or 3 seconds to create movement in the ECRL muscle, and then so create movement in the tendons also. Now, one thing we did in the models was that to focus the study on just how the ECRL muscle creates movement in the fingers, we simplify the model by removing as much of the other musculature as possible. Okay, and then we added some joint stiffnesses in the joints to provide some resistance to muscle movement, and this really simplified our simulation process because there were just fewer muscles for the system to simulate. And I hope that answers the question.
Yeah, so I have a follow-up question actually. So since you have experimental data from cadavers and then you did your simulations, have you done any work to compare your simulated results to what you observed in the cadavers as far as the movement of the fingers for the 2 different procedures?
We have only done it qualitatively, as I have shown here. Okay. So in the simulation, you notice that the fingers did not slip on the object. Okay. Whereas in the cadaver, the fingers slipped on the object, which is reality. Right. Now, it is quite challenging to simulate contact and slip, in software, and that is something that we will be looking into by changing, some of the parameters of the contact model in the dynamic simulation, and hopefully then we can get closer to cadaver data. So I am with you guys on this. I would like to make my simulation as close to reality as possible, and so that I can avoid having to take 10 days off and go to Seattle and have to do the cadaver experiments. So this is something that I will try to do.
Okay, so we have a couple more minutes for questions. So audience members, if you have more questions, go ahead and get those in. So a follow-up question to what we were just talking about this is from Dustin Crouch. You started to mention modeling slipping in OpenSim. Is this something that you're currently developing, a slipping mechanism for the fingertips in simulation?
Yes, we are looking into this.
Can you speak at all to how you might try to model it?
So, I mean, for the full details, you should ask my student because he's the one who's doing it. But there are 2 or 3 contact models in OpenSim, and right now, so there are 2 or 3 like contact models referring to the stiffness of the fingertip and like the friction coefficients and so on. So those are the main parameters that we will tweak in OpenSim. We don't know. We don't have a full handle yet on which parameters, what values those parameters actually are.
Okay. So how did you set the contact parameters that you're using now? That was another of my questions.
Yeah, I think again you have to ask my student exactly about this, but I think we just set the stiffness in the fingers to be high, okay, and we set the friction coefficient to be very high as well.
Okay.
Okay, so obviously that's not as close to reality as we would like, but I mean our focus is the mechanism design itself primarily, right? And so we have been concentrating our energies on like the suture based and pulley based and seesaw mechanism based, and so now that we have got one result, a few good results under our belt, we'll start tweaking with other aspects of the solution.
Okay, that sounds great. If there are no further questions from the audience, I think we'll go ahead and wrap up the webinar. If you can advance to the next slide for me, Ravi. I want to acknowledge our funding sources. So OpenSim and this webinar series are supported by several grants from the NIH, including a grant that funds our National Center for Simulation and Rehabilitation Research. We're also supported by the DARPA Warrior Red effort. So I really want to thank Ravi again for a great talk and the audience for all of your great questions. Next slide. So you can find information about the center, upcoming events, and other resources for the OpenSim community. Just go to opensim.stanford.edu. We also ask that you please complete the survey that's going to appear in a pop-up window at the conclusion of the webinar. This will help us improve the webinar series and help us identify topics for upcoming webinars. So again, thank you all for participating. And we hope you'll continue to stay involved with the webinar series and with the OpenSim project.
I just wanted to quickly thank Jen, Joy, and the NCSRR and OpenSim team for giving me this opportunity to present to the larger OpenSim community. I'm extremely thrilled with the opportunity to use, with the availability of OpenSim for all of us. And really, while I presented the cadaver data first, we used OpenSim, I mean in this talk I presented cadaver data first, we used OpenSim to do the first analysis. And that gave us confidence to you to perform the cadaver studies. And also the OpenSim team has been very helpful to us to sort out all the bugs that have happened. I mean that occur when we are exploring this problem. And I thank Jen, Scott, and all the other OpenSim team folks for helping us with this.
All right, thank you so much, Ravi. We're excited to hear about the future of your project too. Okay, thanks everyone.
Thank you.
See you at the next webinar.